All right. So what I'm going to do is find the integral from 1 to infinity of x over x squared plus 1 dx, which we think of as the same thing as the limit as a approaches infinity of the integral going from 1 to a of x over x squared plus 1 dx. All right. So again, positive function, check. Continuous function, yes, it doesn't have any vertical asymptotes, poles, or anything like that. Decreasing, that's what I was talking about before. All right. We transformed a sub n into a function of x. Now we're at the point where we're going to find the integral. Now, based on this information, we're going to be able to make a determination of whether or not both the integral and the original summation, the series, will converge or diverge. All right? So, here we go. Limit as a approaches infinity. Now, this is some variation of a natural log, ln of x squared plus 1. And the way I know that is because if I take the derivative of the bottom, I get a constant multiple of the top. Derivative of the bottom is 2x. Well, I really only want 1x, so let me pop a 1/2 there. All right, and that's happening over the interval of 1 to a. All right, you could use u substitution if you want, but a little u sub on the fly is probably a little bit better for something like this. All right, then it becomes the limit as a approaches infinity. You can write them in radical form if you want. I don't think it's necessary. 1/2 ln of a squared plus 1. I don't need absolutes. Most of the time I would, but I don't in this case because it's going to be positive no matter what. Yeah, it's squared. Squared and a sum. All right, sum of squares are always positive, in which case the absolutes are unnecessary. Although, as we've seen throughout the course, the absolutes, they don't make the differentiation process any more challenging. Whether you put them in or not, it's not a big deal. So now I have to evaluate this, right? Well, this part's constant, right? So then the question becomes, all right, what's happening here? Well, a log function is an increasing function. And there's nothing about this to make me think anything different. I mean, you could write it in its other form, which would be the natural log of the square root of a squared plus 1. You put it in your calculator if you want. Look at the picture. But if you think about what a log function looks like, a natural log function, you're looking at something like this that increases without bound. It increases very fast early on, but down the line it slows down in its rate of increase, but it never stops increasing. All right, which means that as I go further and further to the right, I'm still going up to an infinity. I'm just not going to get there. I'm not going to get to the y infinity as quickly as I'll get to the x infinity. I'll get to some kind of infinity. It just won't be as great as the x infinity. All right. So infinity minus a constant is still infinity. Therefore, we're looking at a divergent situation. All right. So that's telling me that the integral diverges, but because it goes hand in hand with the series, I now know that this series diverges. Always tell why it's diverging by the, you guessed it, EIT. All right. Other Calc teachers will lose their minds when they see that notation. IT, PTT, LCT, you know what that is. It's, I think they're getting bent out of shape over it. Right? Like, what the hell else is it? Information technology? No. It is not divergent by the information technology department. So, it's a little bit of common sense here. And in all honesty, I mean, I've had This is absolutely true. Straight A student, like 100 on every assessment. Sometimes 100 because of the bonus, but still 100. You know, like anytime you get anywhere near 100, bro. Diverges by the interval test. Did I take off? No, of course not, because I'm not a jerk. I know you meant to write the integral test. You wrote the interval test. Why? Because you're taking a test and you're nervous. And you accidentally put a V. And also swapped it with the R. But still, I mean, like, you wrote the wrong word, not because you didn't know what you're doing, but because you accidentally wrote the wrong word. That does not cost you any credit. So if I'm not taking off for writing the interval test, then I'm not taking off for writing IT. Right? Although other people will. So, enjoy Calc or differential equations. So it diverges, yay. Now the nth term test, you might have tried that. I didn't try it. Why? Because this section is called the integral test. So we're doing it with the integral test. But also because it wouldn't have worked. If I took the limit of this as n goes out to infinity, what do I get? Right, and then using L'Hopital's rule, 1 over 2 to the nth, right? Plug in the infinity, you're getting 1 over infinity. 1 over infinity goes to what? 0. The nth term test, that's like the one thing you don't want it to be. Because if it's anything other than 0, it means it diverges. If it is equal to 0, it means it's inconclusive. It could converge or diverge. Now here, as it turns out, it diverges, but not by the nth term test. Okay? So nth term test would have let you down, although it wouldn't have been hard to do. Same deal here. You try the nth term test, plug in an infinity for the n. 0. All right. Nth term test failed. Now I try something else. Next thing down the line would be the integral test, and that's where we are. So, going from 1 to infinity, and you can cut out some of the fluff here too, obviously. 1 over x squared plus 1 dx. You know, because if you know that you're taking the a sub n, converting it into a function of x, and then taking the antiderivative of that function of x, why can't you just go right to the antiderivative, right? And in fact, if you really want to get fancy, you know, if you're going to cut corners, cut them all, you know. You could write the intermediate steps too if you want. I don't require it. It doesn't matter to me. It's not a formal proof. All right. Sorry, just got to double check. So, I need to integrate this guy here. I'm going to have the limit as a approaches infinity. And what is the antiderivative of 1 over x squared plus 1? Not ln. Arc tan. Derailed by inverse trig. That's pretty common. When it comes down to this part, you know, like you get to this unit, like, oh, okay, I know in this situation I use the geometric series test, then I use the integral test, then I use the direct comparison test. And then I get my setup, and I have an integral, and I look at it, and I'm like, ah, schnitzel. I don't know how to take the integral, but I don't know this one. So you did all that other work, and now you're like, limit as a approaches infinity from 1 to a of blank. And then that's what you're staring at for the next half an hour, waiting for divine intervention. It doesn't always come, unfortunately. At that point, the best you can do is tell me what you would do if you knew what the antiderivative of 1 over x squared plus 1 was. All right. There was a lesson sheet. I don't know what page it was, but it was titled 3 Similar Integrals, or part of it was titled that. I found that as a student, because that came out of the Larson calculus textbook, And that little section hasn't changed since the first edition. I think they're on the 12th edition now. So I had that textbook when I was a student. That helped, that little section in that textbook helped me immensely. But specifically, those three problems, just looking at those three cases and saying, wait, okay, so they look the same, but they could be three different things. And the three different things were the disguised rule versus the inverse trig versus the natural law. And really, I didn't even have to understand necessarily what to do, as much as I had to know that when I see these types of problems, it could be one of those three courses of action. So I try the natural law, okay, that didn't work, it's probably inverse trig rule. So then I know to look to my note card and I'm good to go. All right? So it's the little things like that that it tends to make a big difference. Or at least it did for me. That's all I can offer. What worked for me? Not going to be the same for everyone. Arctan of A minus the arctan of 1. But I didn't really become a beast in math until I learned the unit circle. I mean, I always had a sense of it, but like to understand it, like in its entirety. Like the ins, the outs, the y's, and things like that. So I'm only really going to find the limit of this because arctan of 1 is a constant, hence the unit circle connection. Arctan of 1, well, the ratio is 1. In the unit circle, where is tangent equal to 1? Somewhere. Well, it's like the world's biggest multiple choice question. There's like close. So you're in the right quadrant, and you're actually one away from it. So 45 degrees. But we're going to say pi over 4. All right. The ratio for tangent is equal to 1 when sine and cosine are the same. That happens in two places, pi over 4 and 5 pi over 4. All right. But the 5 pi over 4 is in the negative interval, so for two reasons it's not relevant. One, because we're typically living in the positive realm for this topic, but also the domain for tangent is consistent, or inverse tangent is consistent with inverse sine, which only exists from negative pi over 2 to pi over 2. Right, so fourth and first quadrants. Anyway, as it turns out though, that part's not 100% necessarily relevant, because you're not really going to do much unless you can figure out not this part, but this part. All right? So that's the big question. So I do want to actually try. I just hit pause on it. A little time jump. All right, so you can go back into function mode. Calc 3, you're going to be bouncing back and forth between function mode and parametric and polar mode anyway, so get used to it. Degree mode, radian mode, it all depends on the mood of the day. Arctan, so inverse tan. Put it next because we're looking at a function. And maybe just a quick old zoom trig. See what's going on. Zoom 7. Oh, it appears to be leveling off. I wonder where it's leveling off. In order to get some insight as to where it might be leveling off, you may want to consider a tangent, an ordinary tangent function. Y equals tangent of x. Just one full cycle, if you can call it a cycle for a tangent function. It looks like this. So it approaches those two asymptotes, right? So I have two asymptotes that only occur when tangent is undefined. Well, tangent's only undefined whenever cosine's equal to 0. Where in the unit circle is cosine equal to 0? 90 degrees, so pi over 2. And 270, so negative pi over 2. All right. So then when I'm looking at the arc tangent, you have the picture here. It kind of looks like a rotated version. It's pretty close to accurate. All right. So the arc tangent, what was y becomes x. What was x becomes y. So my vertical asymptotes become horizontal asymptotes. All right. And based on looking at the picture, you could agree that that seems to be the case. All right. It still has the same x-intercept. The shape almost doesn't matter because once you realize that the horizontal asymptote is now the relevant part, you know that it must be approaching, sorry, frog in the throat, pi over 2. Because the one on the negative end doesn't make sense. It's not relevant because I need to go out to infinity. So I'm going to the right. So my arctangent function has to be going out to pi over 2. And pi over 2 minus pi over 4 is pi over 2. Oh, pi over 4. Jeez. Yeah, that's a bad mental error. Like a half minus a quarter. Forget the pi's. I like pi though. So again, just going back to the definition, if f is positive, continuous and decreasing, original function seems to be decreasing. I'm increasing my denominator for each increase in n, so my fraction's just going to get smaller and smaller, so I agree with that. If I were to graph the function, you can see that there's a horizontal asymptote. The limit of the integral bears itself out, right? So we're looking at, again, it's either both going to converge or diverge. We've got something that exists, all right? So it doesn't matter what it is, it matters that it exists. All right, keep going off the page. So it converges. Now you got to understand, this is where the function will converge. All right, so as a goes out to infinity, the accumulation of area will converge on this particular value, pi over 4. So when we're talking about area over an interval from 1 out to infinity, because it's a decreasing function with an asymptote, we're going to close in our area is, as we increase our x value, getting closer and closer to pi over 4 as the true area bounded under that curve. All right? Any experience with a normal distribution, this is actually how the area under a normal curve is determined if you want, using this exact process. All right? So what does that tell us? Well, this is a continuous function. This is not a continuous function because this only exists for discrete values of n. 1, then 2, not 1.5, not 1.8, not 1.99, just 1, then 2, then 3. How can you capture area under disconnected points? There's no boundary there. Okay? It's like a boat with a screen at the bottom. Alright? What boundary do you have to hold out the water? It's not going to do anything. Alright? So all this gives us is an approximation of what the area would be under the curve that most closely models this series. All right, so what we're getting is the idea that if this is going to be an overestimate of that series, and this converges on a particular value, because it's kind of like the sandwich theorem, because this is contained within this curve, then if this is closing on a particular value, if it's squishing into a particular value, whatever is trapped within the function is also going to be converging on a particular value. All right, it works almost exactly conceptually like the squeeze theorem, and so that's kind of why we talk about things like that, at least in part. Okay, so that'll do it for today because that was plenty. So that was page 76 times. And also,